bringing you an explainer that is literally all about the foundation of everything. From the macroscopic world that we can actually see and touch, all the way down to the microscopic particles that build it, we are going to explore what makes up the universe around us.
Okay, let's dive right into this. You know, Nobel laureate Roald Hoffmann put it perfectly. He said, chemistry isn't just some static periodic table of 100 or so elements. Not at all. It's the infinite code of reality happening all around us every single second. It is the science of the infinite variety of molecules that can be built and transformed. I mean, from the curd forming in your kitchen fridge to the rusting of an old iron nail, this highly dynamic science is constantly at work.
Chemistry is deeply fascinating because it didn't just pop up overnight. It actually evolved out of some surprisingly ancient and honestly somewhat mystical beginnings. Between 1300 and 1600 CE, the birth of alchemy and itrochemistry was driven by two massive, legendary quests: finding the Philosopher's Stone, which people thought could turn base metals like iron into solid gold, and creating the elixir of life for true immortality. But if we look even further back, ancient India was incredibly ahead of its time. Right around 600 BCE, an Indian scientist named Acharya Kanda conceptualized atomic theory centuries before John Dalton even came along. He proposed that matter is made of indestructible particles called paramanu. We also have ancient Ayurvedic texts, like the Charaka Samhita, discussing the reduction of particle sizes. I mean, that is basically what we call nanotechnology today.
Let's ground ourselves in the present day for a second. With all this wild ancient history, you might be wondering, why do we study chemistry today? Like, how does it actually anchor to our modern survival?
Well, the short answer is that chemical compounds are absolutely critical to human life and technological advancement. Chemistry directly gives us the everyday materials we need for computer components and the fertilizers we rely on to grow our food. But more importantly, it provides us with incredibly specific, life-saving drugs. For instance, therapies like cisplatin and Taxol are totally essential for cancer treatment, while AZT is a vital drug used for helping AIDS patients. But to really grasp how these complex drugs and materials work, we have to strip it all the way down to the base level. We have to look at matter. Matter is simply defined as anything that has mass and occupies space. Books, water, the air you're breathing right now, it's all matter. And it exists in three physical states. Solids have a definite volume and shape with tightly locked particles. Liquids have a definite volume but no definite shape, so they just take the form of whatever container they're in. And gases? They have neither a definite volume nor shape, completely filling up their given space. And what's truly amazing here is that these states are completely interconvertible simply by applying heat or cold. You heat a solid, it becomes a liquid. Heat it up even more, and you get a gas. Cool it down, and that whole entire process just reverses.
How do scientists actually organize all this physical stuff? Well, we start by splitting matter into mixtures and pure substances. A mixture contains two or more substances mixed in any ratio. Now, if it mixes completely uniformly, like sugar dissolved in water, or the air around us, we call that a homogeneous mixture. But if the composition isn't uniform and you can actually see the different parts, like a mix of salt and sugar or grains and dirt, that's a heterogeneous mixture. The really great thing about mixtures is that you can separate them back out using super simple physical methods, like filtration or distillation. Then on the other side, we have pure substances, where the chemical composition is entirely fixed. We divide these into elements, which consist of only one type of atom, like pure sodium or oxygen gas, and compounds, which form when two or more atoms of different elements combine in a strictly fixed ratio. Water, or H2O, is the perfect example. It's always two hydrogens to one oxygen. And the ultimate irony of chemistry is perfectly displayed right here. A compound's properties are totally different from its individual elements. Think about it. Hydrogen burns with a pop sound, and oxygen actively supports fire. Yet remarkably, when you combine them into the compound H2O, you literally get a fire extinguisher.
Shifting our focus now from just defining matter to how we can universally measure its unique characteristics. So, the crucial point is understanding the difference between the two types of properties every single substance has. Physical properties are things you can observe or measure without changing the substance itself, like its color, its melting point, or its density. Chemical properties, on the other hand, require an actual chemical change or reaction to be observed, such as testing a substance's acidity or its combustibility.
To study these properties quantitatively in a lab, scientists realized they needed a unified language. Historically, the world was split between the English system and the metric system. So, to prevent massive global confusion and to standardize research everywhere, the scientific community officially adopted the International System of Units, or the SI system, back in 1960.
This entire system is built on 7 SI-based quantities. I highly encourage you to make a mental note of this, maybe even grab a screenshot, because it is the absolute foundation for all lab calculations. You have length in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in kelvins, amount of substance in moles, and luminous intensity in candelas. Literally every quantitative measurement in chemistry builds off of this exact list.
Let's move to and see how this builds. Because chemistry goes from the macro to the micro, scientists use specific prefixes to handle incredibly large or incredibly minuscule numbers. These range all the way from yocto at 10 to the power of -24, all the way up to yotta at 10 to the power of 24. Day to day, you'll frequently rely on prefixes like micro, milli, and kilo just to keep your calculations clean and manageable.
We're going to focus on 4 key properties that are calculated constantly in a laboratory environment. First, we really need to clear up a frequent confusion: mass versus weight. Mass is the actual amount of matter in an object, and it stays perfectly constant no matter where you are in the universe. Weight, however, is the force exerted by gravity on that object. That means it can change depending on your location. In the lab, we want true mass, which we measure super accurately using an analytical balance.
Next up, we have 2 core spatial concepts: volume and density. Volume is simply the amount of space an object occupies. While its official SI unit is meters cubed, in chemistry labs we typically use liters or milliliters. Density is mass per unit volume. It essentially tells us the exact physical crowding of particles within a specific volume, showing us exactly how closely packed those particles really are.
The 4th key property is temperature. There are 3 common scales you are going to encounter: Celsius, Fahrenheit, and Kelvin. Standardized mathematical formulas allow us to easily convert and jump between these 3 scales, depending entirely on the requirements of our experiment.
Now, what's really interesting about this slide is the distinct difference between the Celsius and Kelvin scales. While you're likely super familiar with the Celsius scale allowing for negative values, like a freezing winter day, the Kelvin scale is an absolute scale. Because of how it's calculated, a temperature on the Kelvin scale can never, ever drop below 0.
We've built a really strong foundation today, going from ancient atomic theories all the way to standardizing global lab measurements. But it leaves us with a pretty compelling thought. When even our most basic measurements get this complex and require this much exactness, how do we handle significant figures, precision, and the ultimate laws of chemical combination? Well, that is exactly what we will explore next time. Keep focusing, keep learning, and thank you so much for joining this Explain.